Good morning, friends. We will be continuing the lateral directional case. We are trying to get interpretation via the roots of this characteristic equation. And you know all this A, B, C, D, E, they can be easily computed once I know lateral directional dimensional derivatives. And we have seen generally for most of the aircraft, you get roots like this. One is slowly convergent root, a real root, highly convergent, a real root, with negative sign, and slowly damped Dutch roll, it's like oscillatory roots. We'll now try to use this equation or this matrix equation and take the determinant 0 to find the characteristic equation AS4 plus BS cube plus CS squared plus DS plus E equal to 0. We'll now simplify this for spiral, roll, as well as Dutch roll mode. And these are approximations. Mostly they are not very good approximations, but still it has got some relevance to the designers in an approximate manner. It helps a lot. So first we will try to do a roll or spiral. First we will do spiral approximation. Before we go for a spiral approximation, let us remember, before we go for a spiral approximation, please remember we found out a condition L beta NR minus N beta LR greater than 0. Remember, this was from the condition E greater than 0. We said if E is greater than 0, then it will not suffer from any spiral mode divergence. Right? First of all, let us understand what is a spiral mode. The airplane, if there is a bank disturbance, the airplane goes to a side slip. As it side slips, if it is a stable airplane, directionally it turns like this. As it turns, there is a R, yaw rate, that will also give a moment, a rolling moment, because as it does like this, you could see from the vertical tail is pushing the air towards my left hand side, so it gets a force on the right hand side, so that also gives a rolling moment, which further banks the airplane, and then further there is a beta, further there will be turning. So this sort of a combination will go on unless and until you have got CL beta, that is, as it banks and side slips, and CL beta tries to recover it, right? So you see that the L beta, where it is actually non-dimensional, is CL beta, and CL beta is less than 0. What is CL beta? CL beta is again bank, side slip, and it tries to come like this. So CL beta negative. NR, you understand what is NR. In NR, you have got CNR, it is the yaw damping, it is negative. Then N beta, it is Cn beta. For a directional stable airplane, Cn beta has to be greater than 0. And this is CLR. And CLR, you understand, if the airplane is having a yaw rate like this, let's say, if I try to explain you, if this is the vertical tail, this is the airplane, is having a positive yaw rate like this. As it goes positive like this is pushing the air this direction. So it will experience the force in this direction, and this force into the distance from the fuselage center line, that will give me a rolling moment. So vertical tail contribution to CLR is also positive. So now it is not sufficient to know the signs. What we need to design the airplane in such a way that this L beta into NR minus N beta into LR, this should be greater than 0. That is important. Okay? So we understand who are the non-dimensional derivatives. They play the role. We also understand how do I change the CL value of CL beta, and if I increase vertical tail height, CL beta will increase. If I make it a high wing, CL beta will increase in negative sense. Like that, the designer, I should know if I want to tweak this parameter, which are the design parameters I should change, which are geometric parameters I should change. So this should be very clear before you go for spiral approximation. And I again caution you that these approximations are generally not very good approximations. Still, they are good enough for a designer to get some feel for basic design parameters. So now we'll be talking about spiral approximation. Before we go for spiral approximation, please also understand that the aerodynamic forces do not largely depend upon phi or psi. Please understand, we are aware for normal case the aerodynamic forces will not depend upon phi or psi, right? Please understand the aerodynamic forces do not depend upon phi and psi for normal case. It is a fair assumption to believe that aerodynamic forces depend on phi dot, psi dot, and beta. Okay, you can understand why phi dot. You see, if it is phi, the aerodynamic force has nothing to do because the relative airspeed. Okay, that matters. Whether it's going like this, or going like this, relative air is same. However, phi dot is this. As there is a phi dot, there is a relative air speed vertically up. That gives the aerodynamic forces. Similarly, psi dot, there is a rate. So that will also give a induced beta, which will give you forces, aerodynamic forces. That is why it is important to first identify this. And then, if we now try to simplify, which I am again cautioning you, it is not a very good approximation, we have to incorporate this understanding into this matrix. And remember, instead of psi s, we are telling the variable is psi dot. If it is the variable is psi dot, then naturally, if I write it here psi dot, so 1s will go from here, which I have done last class, and here this s will go, and here also 1s will go, right? Because this into this, this into this, this into this. And also now what we do, we say phi, it doesn't matter with phi, so this term into phi, this term into phi, this term into phi, this I drop this, because phi is not relevant for us. What we are left with is this one, L beta into beta, this into psi dot, then n beta into beta, s minus nr into psi dot by ds. I am dropping this, I am dropping this. Because I am saying in a spiral mode, what I am focusing is bank, side slip, this, further bank, this, like this. So I am neglecting the effect of any force acting on the y direction. Again, this is an approximation, right? I am more talking about the angular motion. Okay? So this is also dropped as if it is taken care, right? Or not so important. This is an approximation because when I talk of spiral mode, I am talking about bank, side slip, this, further bank, like this. And though there is a slight force will be in the y direction because beta is introduced transient manner, but we are neglecting that. Okay? So we are having a smaller determinant which will be having a structure like this, L beta SA1 plus LR minus N beta S minus NR, this is equal to 0. That becomes my determinant, that becomes my characteristic equation. And if I do this, if I now expand this, I will find L beta into S minus NR, you see this one, minus N beta into SA1 plus LR. This is equal to 0, which gives me value of S as L beta NR minus n beta LR by L beta. Okay. And now see, to make sure that the spiral mode is convergent, not divergent, so this man should be less than 0, right? Okay, and what is the sign of L beta? L beta, you know, as CL beta, right? It is constant into CL beta, CL beta rolling moment. And what is the sign of CL beta? CL beta is negative. So for S less than 0, L beta into NR minus N beta into LR has to be greater than 0. Please understand this condition to be less than 0, and since this is negative, so this gives me a condition which already we have seen, L beta NR minus N beta LR greater than 0. Okay? So this also we are getting from first approximation. But the question comes, okay, it will tell you whether spiral mode is divergent or convergent, but how accurate it will be in terms of number. So if we do an approximation with the data which we have used, last example for this airplane, then you get the value of S as minus 0.0065, which means TS 1 by S minus. So that will be 1 by 0.0065, and this is equal to 153.8 seconds. But exact solution was 991 seconds. Do you see how much different? Right? So once we try to talk about quantitative manner, this approximation does not give you a very good result, very far off result. But fundamentally, as a designer, it yields what we got from exact solution, that E greater than 0, that L beta NR minus N beta LR greater than 0. Similar by this approximation also, we got same result. So that is the beauty of this approximation. And that is the reason, even if the numbers are not close, we still continue to understand that to get feel for the designer. Okay? So this is the spiral approximation. Now we will come to roll approximation. Now we will talk about roll mode approximation. And what is this roll mode approximation is, if the airplane, remember for lateral directional case, we have identified there are 3 ways the airplane will get generally excited. One is spiral mode, like this, and that is roll mode, right? Okay? Okay? And that is Dutch roll. These 3 modes. Now we are talking about roll mode. That is, if I give a disturbance in the aileron, how this aircraft is going to respond to this rolling moment disturbance, right? What is the approximation done here is, the assumption is, if it is rolling like this, it is not affecting any motion in the y direction, no beta is introduced, and no psi dot is introduced, only phi, one dimensional. Right? Okay, it's equivalent of thinking in a tunnel, you are given a roll disturbance and it is trying to build or decay, whatever it is, right? If you are doing only one dimensional roll mode approximation, then you could easily see only you are keeping this. So S square minus LPS into phi of S by delta of S equal to L delta A. All, no yaw motion, no side slip motion, so only this. One dimensional roll, so I can write S square minus LPS into phi of S by delta, now delta A, aileron input is equal to L delta A, right? Or let me write it, yeah, L delta A. I can write capital for clarity, L delta A. Now if you see carefully, this I can easily write phi of S by delta A of S is equal to L delta A by S square minus LPS. So you are expert now. The characteristic equation is S into S minus LP equal to 0. So you have got S equal to 0 and S equal to LP. S equal to 0, neutral stability as far as phi is concerned. I told you again and again, whether plane going phi 0, phi 10, phi 30, aerodynamically they are neutrally stable, there is no change. So if forget that, S equal to LP, it only suggests you if LP is negative, it will have a first order response and it will be convergent response. And what is LP? LP, you know, is having CLP in its term, and CLP is roll damping, which is less than 0. Just to recall, if this is the airplane and if it is having a roll, say P in like this, then at every station there will be relative airspeed, which will induce angle of attack as it is moving forward. So when ulta will happen, reverse will happen here. This will give you a rolling moment like this. So this is the roll damping, because the rolling moment is proportional to the P for simple reason. This induced velocity is proportional to P r bar, which is at a distance r bar from here. So this moment is proportional to the rate. So we say this is roll damping. So this is the important root I have got. As long as this is negative, it is convergent. And now I need to solve this to find out time history of phi. How do I do that? Let us do some numerical search on this expression with the roll mode approximation. This is roll mode approximation. And once we solve that characteristic equation and put the values, we get S equal to minus 0.437 seconds. And the TR is 1 by this, so this is 2.29 seconds, which is coming from approximation. That is 1D approximation, right? But exact value was 1.972 seconds. You see that they are not that bad as spiral, okay? Now the question is, if I want to know how this bank angle is developing, then this is my transfer function, phi of s by delta of s. I can always find out the time history by using a partial fractional method, and you will find that from here I can write phi of t equal to minus L delta into delta by LP plus L delta into delta by LP square e to the power LPT minus 1. I am sure you know how to find out from this to time domain, which we call inverse Laplace transform, right? Which is straightforward. Once you get this, you also know what will be the roll rate in frequency domain. Roll rate, we make an approximation P equal to phi dot. So P of s equal to S phi of s, right? And phi of s expression is this. Phi of s is L delta by S minus LP into delta of S. So this is straight S phi of S. That will be L delta A by S minus LP. And this is, of course, delta A will be there. Delta A, right? Okay. So once I know P of S is S phi of S, and phi of S expression already I know. So this is my P of S. So I can easily from frequency domain, I can go to time domain by doing inverse Laplace transform. So this will come out to be this. Okay. So what are you seeing in this expression? E to the power LPT. LP is what? Positive or negative? LP is negative. So as time increases, this man will vanish. So you will get a steady state value, which is minus L delta into delta by LP. Right? So once you give an aileron input, it takes some time to go to a steady state value, okay, which is here. Clear? So you can easily use this to find out the steady state values, how much the airplane will respond for different types of aileron input. This I am completing just to give you a little feel how to estimate approximately the response. Okay. Now we will complete the last part, which is the Dutch roll mode. physically what is it? As we have agreed that airplane generally in lateral directional case can get excited into spiral, roll and Dutch roll. Dutch roll is primarily this one is going on, see, yawing like this, and also this motion, right? Although there will be some bang disturbances, but primarily this and this. This is the Dutch roll. So you go like this. Okay. And this been approximated using keeping only this fourth term, and with beta and psi, no psi dot. Please understand. Okay. And the determinant is typically we have SU1 minus y beta, SU1 minus YR, and here it is minus n beta and S square minus SNR. This is equal to 0. Okay? Because we have assumed that there are no phi disturbances. So you could see any term with phi, they anyway vanishes, and all the second part, which was primarily phi equation, is also taken out. These are approximations, good or bad, we will understand now. And if I do like this, I get a characteristic equation as S square minus S into NR plus Y beta by U1 plus Y beta NR by U1 plus N beta minus N beta YR by U1. Let me check. It is S square minus S into NR plus Y beta by U1 plus Y beta NR plus N beta. So there will be bracket here. Okay? That you can easily find out by doing this and this, right? If this is again the characteristic equation for Dutch roll mode approximation, so let me write here approximation then you could see that S equal to 0, again it belongs to a neutral stability because the yawing motion, again psi this way, that way, it is all aerodynamically similar, so we forget that. So we get again second order equation of the form mass spring damper system. So you can easily use this and write omega n Dutch roll as 1 by U1 into Y beta NR plus N beta U1 minus N beta NR. Right. And zeta Dutch roll as minus 1 by 2 omega ND to NR plus Y beta by U1. This you can directly find out from here because this is nothing but your omega n square. Now we will try to see how much we get in terms of numerical value of omega nd with approximation and zeta nd with approximation, and we will see how they compare with the exact solution. If we see omega nd, we will get around 1.62 radian per second if you put the values, and zeta you will get 0.058. This is the zeta value. One thing is very clear from this approximate value also, it's a low frequency, and zeta nd is 0.058 means weakly damped. Okay? But what was the exact value? Let us check it. The exact value was omega nd was 1.618 and zeta as 0.036. So you could see as far as omega is concerned, not that different, but zeta is also close, not that bad. But the problem what happens, nowadays, if all the airplane, there will be lot of large value of Ixz and all, cross moment of inertia. In that case, this approximation is likely to fail very drastically. Okay? So this I thought I will complete it because finally we are going for stability augmentation system. So few things you should be clear that if I want to increase the Dutch roll damping as a designer, what do I do? This is y beta by u1. So I will not focus here. I will try to see how can I increase NR or how can I increase CNR. Okay? And how CNR can be changed by either changing the distance from the vertical tail aerodynamic center to CG or the area of the vertical tail or tail volume ratio of the vertical tail. To have those ideas, I thought we must complete this before we jump into stability augmentation system. Right? Thank you very much.